My name is Ranger Kwong, and my project is about the effects of functionalizing activated carbon surfaces on carbon-based supercapacitors. My work was done at Dr. Julia Laskin's Purdue laboratory, and thus I will indicate exactly what I did and found independently. Supercapacitors are a type of portable energy storage that are critical in our daily life when everything from your printer to military vehicles require quick and convenient energy. While supercapacitors can charge and discharge energy quickly, they don't perform as well in terms of bulk charge storage. So how do we remedy this problem? One conventional way is to increase the surface area of the electrode that can hold charge. Porous activated carbons are a common choice, as they can boost surface areas by over 1,000 square meters per centimeter squared of surface. Another method is by adding chemical species onto this carbon material. Chemical species can add redox reactions, which can supplement the charge with additional electrons. My project deals with increasing energy densities of supercapacitors by modifying their electrodes with carboxyl and alcohol functional groups. Now, the reason why I became fascinated in this project was due to the usage of chemical reactions, not physical transformations, to improve energy storage design. In order to conduct the experiment, I needed to first make a supercapacitor, and there were three main steps to this. The first was to deposit the two functional groups onto commercially purchased YP50 activated carbon. After functionalization, an infrared spectroscopy scan validated the presence of the carboxyl groups. In this example, the presence of CO bonds and COO bonds indicates the presence of carboxyls after functionalization. The second step is creating our electrode with the functionalized carbon by pasting them onto a disc-shaped carbon paper substrate. And the third step is to assemble the entire device by sandwiching an ionic membrane between two of the electrode disc plates we created in step 2. The ionic membrane provides the free-flowing ions that can flow from one electrode to another during charging and discharging. I independently fabricated the supercapacitors with basic instructions from my lab. With the devices fabricated, 2 tests were done to analyze their performance, which is evaluated based on specific capacitance calculated by the third formula, where M is carbon material mass, and C device is found with machine potentiostat readings. These 2 tests were taught to me by my designated supervisor. However, I conducted all the tests and analyzed the results myself. First, a cyclic voltammetry or CV test was performed, where the voltage of the device was scanned back and forth between plus minus 0.5 volts while measuring the current running through the supercapacitor. As shown in figure 4, the modified carbon devices had a larger range of capacitance, which indicates a higher energy density. However, the shape of the capacitance curve for the modified devices were less rectangular, meaning that they responded slower to a quick change in voltage. I also measured capacitance at different voltage scan rates, some fast, some slow. Figure 5 shows that at low scan rates, both functional groups completely outperformed the pristine carbon counterpart, with alcohol doing the best. However, at higher scan rates, the capacitance of functionalized devices degraded more quickly than the pristine counterparts. Both figures suggest that the functional groups are providing redox reactions that boost performance, but the reactions are not able to keep up with the high rates of voltage scans, and thus cannot sustainably boost capacitance at those rates. While the first test was done by holding the voltage scan rate constant, the second test of performance was the galvanostatic test, where I charge the supercapacitor with a constant current and measure how long it takes for the device to charge or discharge to 0.5 volts. Figure 6 shows that at the current of 0.4 milliamps, the functionalized carbon devices took longer to charge up, indicating a higher energy density that they held. In addition, I also measured capacitance at different charging currents. While at low current densities, the functionalized carbons hold more energy, this increased energy density is lost at higher current densities. Again, this suggests that at high currents, the redox reactions may not be fast enough to provide an extra boost and keep up with the high cycles. In summary, my experiment supports my hypothesis that the functionalization of carbon electrodes with carboxyl or alcohol groups can increase the energy density of supercapacitors. However, the benefit in energy density is not as pronounced at high voltage scan rates or high current densities. I also wish I could have overcome certain limitations in my research, including the largest one being I wasn't able to validate the functionalization of alcohol-modified carbon due to machine failure. In the future, I will try to overcome this limitation as well as see how functional groups may retain deposited large redox ions onto the surface of the electrode to allow for further redox activity. I would also like to thank Dr. Julia Laskin and her graduate students